next talk today will be given by Irit Dinur from Weizmann, and she will talk about PCP.
Okay. All right. So this is going to be a three-part mini course on probabilistically checkable proofs. So we'll have one now, an hour tomorrow morning, and an hour the next morning. So my the outline for the three talks are going to be, my goal will be, I guess, to prove basic PCP theorem and push it as far as we have time. So today we'll just do some introduction and then discuss the connection between PCPs and inapproximability. And I want to show one PCP theorem that goes by the following buzzword. At this point, these symbols don't mean anything to some, and those who know what this is probably don't need to attend this talk anyway. So this will be today. And then tomorrow and the day after, I'll talk about proving the basic PCP theorem by the gap amplification. So this will be like part one, and then in the third lecture it will be part two. Plus, in the last talk, I'll also talk about the PCP composition. And hopefully, these three talks altogether will lead us to the hardness of label cover, which was partly what Ryan started out with. Actually, we won't quite reach this, but we'll talk about it today. I will elaborate further. Okay, so I'll start. So today is going to be this. As we talked during the break, so the audience here is mixed, so some of you really don't, some of you have already taught this, so you know this better than I do. So I'm aiming at those who possibly haven't seen this before. Unless everyone has seen it, and then I can talk about something else. So, what? No, okay, good. Okay. Other things? No, okay, just kidding. So, okay. So just kind of for the fun of it, because, I had to bore some of the people, let me tell you a story that's interesting to everyone, and then we'll start. This story is a story that Eli Ben Sasson told me on how he introduces PCPs to a broader audience, and I think it's a really nice story. So he says, suppose you want to check your telephone bill. Okay, so you get your telephone bill from your phone company, and it says a lot of conversations. This took a minute and a half, this took 5 minutes, and so on, and the charges, and then at the end it says, bottom line, you have to pay $200. Okay, and you want to check it, but you're busy, right? And you don't want to, go conversation by conversation and add everything up. So what are you going to do? Right, so the sum of a lot of numbers depends on every single number, right? If you change one number, the sum changes. So in some sense, a sum is a very sensitive function, and there's no way you can verify that a sum of many numbers is what it is without reading the entire input, right? Because a little change of an input already changes the output. So what will you do? Well, one thing you can do is browse the telephone bill, which is something I do personally. I don't know if you do it. Look at the telephone bill and randomly select a few conversations just to check if it's reasonable, if I know the number, if it's reasonable that I spoke this many minutes to the person. Fine, it's reasonable. So I can check that the conversations are probably the conversations that I did speak, but I don't know how to check that the values that are written there really sum up to the number that's written on the bottom. Right, so what we can do, though, is ask the telephone company to give us some more information that will help us to check this, right? So what information can we ask? We can ask, give me not only the final sum, give me also the sum of every possible subset of the conversation. Okay, so if I have some conversation x1, x2, up to xn, okay, so this one was $5, this one was $1, $2, and so on. And I want to know the final sum. Well, I will just ask for every possible subset. Okay, so there's the empty set, there's the singleton, all these, up to 2 to the n possible subsets. For each one, I want the sum, right? So this is 0, hopefully, this is something. I get a long list of numbers. So if it was a few conversations, this is not so ridiculous. If it was a bit more conversations, okay. This is just a motivating example, and in fact, even in this exponentially long list, it's a non-trivial task. If I ask you, okay, you're allowed even to read an exponential, you're allowed to ask the phone company to give you an exponential number of numbers, what numbers will you ask so that this task of checking will be easy? It's not trivial, but anyway, it's not hard either. What you will do is, now that you have the sum for every possible subset, you can check it by comparing two subsets. You have some S1 and S2, and then you can look at S1, maybe the union of S2, or the symmetric difference of S2. And with these sums are somehow related to each other. So you can ask for, you can randomly choose S1 and S2, and then look at all 4 of these, and sum up and see that the sum of this plus this equals the sum of this plus this, right? This should be true if the sums that I were given, what? Intersection, sorry, yes. Right, okay. This should be true if all the sums were given correctly. Of course, the phone company wants to maybe make me pay more money, so it doesn't have to give me the correct values. Maybe it can do something so that even if I do this kind of check, the check will pass with high probability, and yet, in the end, I'm forced to pay more money than I'm supposed to. Okay, so this is what underlies PCP. We can prove, and we'll do it later on, that the phone company can't do much. I mean, this proof is good in the sense that really, if the test passes with good probability, it means that these partial sums must be faithful to the original input, and so I cannot be cheated. Okay, so that's the kind of thing I want to be able to prove. That I want to prove some assertion, for example, that the sum of all these numbers equals some value. The proof, it can be something, whatever I choose. And I want a checking mechanism that looks at the small, tiny part of the proof. For example, here I'm only looking at 4 numbers, which is something that a person can really do without a computer, and add them and check that that it's consistent. Okay, so we'll get back to this maybe in half an hour. For now, I'll leave it on the board. Okay. Now we do Monte. Fine. It stops on its own. Okay. Okay. Where's my piece of paper? Oh, yeah. Okay. Okay, so let's go back to PCPs, and we'll relate to the story later on. So let's start, complexity theoretic point of view. We have the class NP of all problems for which you can easily check a solution. If someone gives you a solution, there is a way to check that this solution is valid. This is not a property of all problems in the world, but this is the property of reasonable problems. At least the least you can do is be able to check a solution if you see. Okay, so this is NP. This is all problems with checkable solutions. For example, three-colorability. You're given a graph, and someone tells you, this graph is three-colorable. There's a way to color the vertices such that every edge sees two different coloring. I don't know if that's true or not, but if you also give me the coloring, it's easy for me to check. Okay, another way to think of NP is that it's the set of all efficient proof systems. Okay, well, efficient proof systems. So what is a proof system? It's some system in which someone can write a proof, and that's the prover, and the verifier can check it in an efficient manner. Right? So we're used to, from grade school, of proofs being a sequence of statements where each one is either an axiom or follows from previous statements. But the proof system can be anything that has some rigorous specification. For example, if you give me a system of equations and a solution, there's a rigorous way of me plugging in the values into the equations to check that all the equations are satisfied. So this solution is a proof that the system of equations is solvable. You give me a three-coloring of a graph, there's again an efficient and rigorous procedure for me to go edge by edge and check that this coloring is legal. So this coloring is a proof that the graph is three-colorable. So in this sense, let me just say, so for example, for three-colorability, the graph is the theorem, and the three-coloring is the proof. So in general, every proof system that you will think of for which it's possible to efficiently check the proof, this defines a language in NP. So these two notions are equivalent. And something very nice is this notion of NP completeness. Which says that one problem, for example, three-coloring is NP complete, is able to encode every other problem in NP. Right? So it's one proof system in which you can express every other proof system. Okay, so each NPC problem or language encodes every other NP problem. Okay, so I'm assuming we all know this. I'm just stressing it because of I want to view it as an encoding. Okay, so if I have a reduction from some problem to three-coloring, it means that I'm able to encode my problem in the language of three-coloring. So when I have this reduction, I can encode my theorems in terms of graphs and my proofs in terms of three-coloring. So in this sense, three-coloring, and this is just an example of an NP-complete language, is universal. It can encode any other proof system. So it's a very strong statement to say that all proof systems can be expressed in one specific way. But we're used to it, so it's not so surprising to us. Okay, and the PCP theorem says exactly such a statement. So when I say the PCP theorem, I mean the theorem proven by Aurora and Safra and Aurora, Alun, Mutwani, Sudan, and Segedi in the early 90s. And this theorem says that every every NP problem or proof system can be encoded by a, I'll do it this way, robust proof system. And I don't have space. I wanted to write robust and locally testable, so let me and locally checkable. So what I mean by this is that is what I'm going to say more slowly, right? So. In a PCP proof system, you have a theorem, for example, a graph, and you have a proof, some string, I don't know, for example, a 3-coloring. And this proof doesn't, to check it, it's not only that there's an efficient procedure that reads the proof and does something and decides if the proof is correct or not. More than that, this procedure is robust and local in the sense that the procedure just looks, it has some distribution over small windows into the proof, say only a few bits, reads this window, and based on the value of this window, it says yes or no. Okay? And on average, over all these windows, the procedure will succeed. So if the proof was correct, the procedure will say yes, always say, and if it was incorrect, the procedure will say no with constant probability. So somehow, if the proof was false, this error will appear in many, many places in the proof. In that sense, the proof is robust. When we think of regular proof, like the ones we write in papers or like an assignment to a 3-sat formula, usually you think you have to check every single bit of the proof because there might be one specific bug that ruins the entire proof. A PCP proof is different in that somehow, if the proof is if the theorem is false, then no matter what proof you write, the bug will be evident in many locations. So formally, we say we have this notion of an RQ restricted verifier. Okay, and this is an algorithm, so I have a picture, right? So we have a picture of this verifier. And the verifier has access to a proof. This is pi. And it also has access to the input. This is some encoding of, let's say, G. It's a graph. And pi is, can be a 3-coloring, but it can be some other encoding of something. I don't know what. Okay, so this is the input. And this is the proof. Okay, and the verifier, when the language is in NP, a language is in NP if there is a verifier which is a polynomial time algorithm. The verifier reads the input. It reads also the proof. And then it decides, and then it says yes or no. And such that if, the input I called it G. If G is in the language, then there is a proof such that the verifier, when it looks at the proof on input G, that's its notation, says yes. And in the no case, if G is not in the language, then for every proof, the verifier will say no. So this is the regular verifier, not the RQ verifier. This is before we added this extra thing. This is just the regular definition of NP. A language is an NP if there is a polynomial time verification procedure that says yes when there is a proof, and if the theorem is false, G is not in the language, no matter what proof, you will always say no. For example, for 3 coloring, G will be the graph, pi will be a coloring, and the verifier will be a polynomial time procedure that just goes edge by edge, right? And then you give it a right coloring, a correct coloring, it will say yes. And if the graph is not 3 colorable, no matter what the proof says, it will always say no. Okay, so now what is this notion of RQ verifier? R is the random coins. And Q is the number of queries. Okay, so you let the verifier toss some random coins because it's only going to look at a small number of bits from the proof. So it must have some way of looking at the entire proof. It will do it on average. So it tosses some random coins, and then it reads some Q number of queries. Let's write it here. If there is a verifier that how will I do? Okay, let's do it here. Reads G, and then instead of here, I will write tosses R coins and reads Q bits from pi, and then based on all this information says yes or no. Output yes or no. Okay, so such a thing is an RQ verifier, and the language is in, and then we say that a language is in PCP R and Q if there is an RQ verifier. Sorry for getting a bit clogged up here. Such that, okay, and then the yes and the no are almost the same. Now the verifier has some randomness. What is the meaning of this randomness? The meaning is that in the yes case, actually, we're looking at the probability over the random coins of the verifier, and here the probability is 1, so it's as if it's meaningless. For every random string, you expect the verifier to still say the right thing. But in the no case, again, we look at how the verifier answers on average, and we want that the verifier, we can't expect that the verifier always says no, but we expect that the verifier says no at least some, I don't know, half of the time. Well, some constant fraction of the time. Okay, so a language has an RQ verifier if whenever the input is in the language, there is a proof causing the verifier to always say yes. And if the input is not in the language, then no matter what proof you give me, so for example, if the phone bill doesn't add up to less than $200, no matter what partial sums you give me or anything or devious that the phone company tries to do, I have a way to check it so that at least with probability 10% or with probability half, say, I will find that there is a problem. Okay? So this is the definition of an RQ verifier, and when a language has such a verification procedure, we say it's in PCP-RQ, and then the PCP theorem says that NP has, for every language at NP, there is such a verifier, PCP, R and Q. PCP log n1. So meaning the verifier tosses O of log n random coins and makes O of 1 queries. So there's an implicit O notation here. It's not really one query, it's a constant number of queries. Okay. Okay. Okay, so the meaning of the PCP theorem, as we discussed, is that there is a way to check every language in NP in a way that the errors somehow pop up. So you only look at the small number of points in the proof, just Q queries, O of 1, and still, if the theorem was false, it will pop up everywhere. And there is a way to translate this to an inapproximability result. So the PCP theorem is just a hardness of approximation. Nothing more and nothing less. So somehow, when you think of it as checking proofs and the fact that a proof can be checked by reading only a constant number of its bits is somehow much more captivating, but it turns out that it's just a hardness of approximation result. And what's the connection? It just says for every okay, let's just write it. It is equivalent to saying that there is a reduction from any L in NP to, I guess, so how is it 1 and 1/2? CSP stands for constraint satisfaction problem with, I guess, Q area constraint over a binary alphabet. What is this thing? This problem, CSP, so forget this, for example. The problem of maximal constraint satisfaction is the problem of you're given a bunch of constraints, C1, C2, up to Cn. These are constraints. Each over Q variables. And so there is some underlying set of variables, x1 through xm. Each constraint specifies which Q variables it's looking at, and it says what assignments to these variables the constraint is willing to accept. Okay? And the question here is find an assignment that maximizes the number of constraints. Right? So in the 1/2 CSP, the question is decide whether there's an assignment that satisfies the probability that it satisfies a random constraint is 1, meaning it satisfies all of the constraints, or decide whether it satisfies at most half of the constraint. Okay, and the reason that this is equivalent is because when whatever the verifier does, so okay, why? Why is this equivalent? Of equivalence. Okay, so suppose this gap 1/2 CSP is NP hard. Meaning there is a reduction, suppose that this is true. there is a reduction from any language in NP to this thing. What does that mean? So for any L in NP, there is a reduction, a mapping, that takes x to some phi of x, such that if x is in the language, then phi of x is a satisfiable CSP instance. Okay, so you start from an NP language, you move to a CSP instance, and if x is not in L, phi of x is a CSP instance only 1/2 satisfiable. Meaning, in both cases, phi of x generates a system of constraints like this, but if your original input was in the language, then there will be an assignment satisfying all of these constraints. And if it was not in the language, then every assignment will only satisfy half of the constraints. Okay, so suppose we had all of this reduction, then I claim, okay, this was all my assumption for my, then I claim that NP is in PCP log N1. And the reason is, now, to prove this, I need to show a PCP verifier for every language in NP, right? That was my definition. And what will be my PCP verifier? It will be simple. You start with your NP language, your favorite NP language, and now how do you construct your PCP verifier? First, you read the input. The verifier is allowed to read the entire input. It's just not allowed to read a lot from the proof. Reads the input and computes this phi of x. Okay? Read the input x, compute phi of x, which is a CSP instance. And then toss log n coins. Based on the value, you select one of the n constraints in your CSP instance. The constraint says, look, I need to know if I'm satisfied, I need to know the values of x1, x2, and x7. Okay, so read these bits from the proof. Okay, and if the value in the proof satisfies this constraint, say yes, otherwise say no. What will happen is that if your original input was a satisfiable instance of L, your new CSP will be a satisfiable instance, a satisfiable CSP, so there will be a proof. The proof will just be the assignment to the variables. It will cause the verifier to always accept. But if you started from a bad input, an input not in L, so it's unfortunate that I used the same letter x here, two different x's. If it was a bad input, then no matter what proof is given, no matter what assignment is given to the CSP, the verifier will reject the probability half. Okay. So this is supposed to show that the formulation of the PCP theorem as a proof-checking theorem and as an inapproximability result is just the same. Okay. So now let's go back to this CSP instance. Oh, you know what? Actually, I'll go back to the first board. Okay, let's do this. Okay, so I have this let's do it this way. NP subset in PCP log n1 is equivalent to the fact that it's NP hard to decide if a given CSP instance is either fully satisfiable or at most, I don't know, half satisfiable. That is satisfiable. Okay? And so I guess when you first look at this problem, it seems that when you look at the CSP to just decide if you can satisfy half of the equations or half of the constraints, it looks like an easy task. Because it seems like a fundamentally different task than having to satisfy an entire system of constraints. Right? But what this fact is telling us is that we have a reduction from the task of fully satisfying a CSP to the task of just telling the difference between these two things. Okay? So the way we prove that this is indeed NP-hard is by starting out with some CSP. For example, I like to think of three colorability. So I have some graph G. And I know that there is one case where it's three colorable, and there's another case where it's, I guess, strongly, or how shall I say it? Blatantly non-three colorable, meaning every coloring. Oh, sorry, actually, this is my first step. Sorry, okay. Either it's three colorable or it's not. Not three colorable. Okay, this is a problem that we know is NP complete. And then we somehow do something to this graph, and we output another graph H, such that H has the property that if G was three colorable, then H is also three colorable. And if G is not three colorable, then H, not only is it not three colorable, but it's what I wrote here before. It's blatantly non-three colorable. Meaning, so here what I mean is that every coloring satisfies or falsifies, I don't know, some 0.0001 of the edges. Meaning there is some small probability, but constant, that if no matter what coloring you give me for H, at least some 0.1% or something of the edges will see the same color on both endpoints. Okay? When we think of a regular NP instance, usually, even if a graph is not three colorable, there's nothing to say that there isn't a coloring that succeeds in coloring all but one edge. It's possible that some instance is not three colorable, and yet there is a way to almost fully color it. Okay? But these transformations, this is the PCP transformation, says that every graph can be mapped into a new graph, such that here, if we were, in the good case, perfectly colorable, then we're still perfectly colorable. But if we were in a bad situation where there was, no matter how you colored, there was one bad edge, then in H, somehow you're guaranteed a constant fraction of edges being bad no matter what coloring you go to. Okay, and the weird thing is that this transformation, the transformation is polytime computable. Okay, so in fact, to prove the PCP theorem, all you have to do is show such a transformation, right? Such a polynomial time computable transformation. Because if you show such a transformation, then you know that since it's NP hard to decide if a graph is three-callable or not, and since you have a way to transform a graph into a graph H such that whenever G was a good instance, a yes instance, so is H, and whenever G was not, then H is blatantly far from a good instance, then you know that if you even had an algorithm that knew how to tell the difference between these two seemingly very distant cases, this algorithm could be applied on H, and its outcome, if it says yes, you knew that G was a yes, and if it says no, you know that G was a no. Okay, so if we have a polynomial time transformation with this property, we've proved this part. And since it's equivalent to this, we've proved the PCP theorem. Okay, so to summarize, it is enough to show a polynomial time transformation, as below, or not exactly below. Okay, so there is this image that you can have in mind that this transformation, we will show an algorithm that does this. It takes G and does something to it and creates H. Now this algorithm sees G. G is just the input. What it doesn't see is whether or not G is three-callable, because an algorithm is limited. It doesn't know if an instance is three-callable or not. Right? So it's seeing G, but somehow you can imagine that it's being blindfolded from the truth of whether G is a good or a bad graph, a three-callable graph or a non-three-callable. So somehow it doesn't see this information because it's computationally impossible to know this. And yet the algorithm somehow works on G, it does something, even though it doesn't know if G is here or here, such that in the end, if G was a yes instance, then it retains the callability. And if it was a no instance, somehow it became much worse. It became very badly three-callable. Okay, and that's without the algorithm knowing which case it was. Okay, so it's like the algorithm is working under the table. It's doing something. It doesn't know if it started from a yes or from a no. It gets something else, and it still works. And the way this works is by somehow encoding the information in G into H in a way that amplifies an error if there was one. Okay, so this should bring us back to this board where we wanted this to encode the fact that the sum of these xi's is some x, such that if the phone company just added one digit all the way to the left and made the sum very large, even if it was only one bit of difference, and so if we randomly test by reading only a constant number of numbers here, we will never see it. Still in the encoding, somehow the bug should be evident everywhere. Remember, so in this picture, what we had this bunch of phone conversations, so it's just a bunch of numbers, and someone claims to us that the sum of all of these numbers, so there is a big sum sign here, equals x. Okay, so there is like a claim here that the sum of the xi equals x. Okay, and to verify it, I want to read much less than n numbers. I want to read just a constant number of numbers. So I ask for some additional proof. Here the proof will be the sum over, the additional proof will be for every subset S. For every S, the verifier will give me some y sub S that is supposed to equal y sub S equals the sum over I and S of xi. right? But this is an adversarial, this is just a proof. Who knows what really is written there? And my goal is to check that somehow, using these partial sums, to check that this assertion is true. And notice one good thing about this proof is that y sub s, for a random subset of numbers, the real value that is supposed to be written in y sub s depends on half of the numbers here. So if you make one bit of change in one number, in your encoding, I view this collection of all y sub s's as an encoding, changes dramatically. Okay, so that's a good thing, because if you think of it here in the way H encodes G, if there was a coloring such that everything was good except for one edge that was upset and falsified, somehow many edges should notice this fact. Okay, I'm saying something that's very informal, but in some sense, each vertex or each edge in H should depend on all of G, or a constant fraction of G. It should be sensitive to all of G, because think of the following two cases. Suppose G was not recolorable, but there was a coloring that satisfies everything except for this edge. You now think of G prime that equals G, except you erase this edge. Now G prime is really recolorable. So this same polynomial time transformation could produce a vastly different graph H, because in the new graph H, so I have here a G prime and an H prime, in the new graph H prime, there should be a valid recoloring. So look at this recoloring. In H, it caused a constant fraction of edges to be falsified. So this means that all of these edges know about the presence or non-presence of this edge. Okay, so this shows that on average, an edge in the graph, in the output of this transformation, depends on constant fraction of the edges here. And similarly here, you see that in your encoding of a sequence of bits by many, many sums, you see that at least we have this property that each partial sum on average depends on half of the bits. So you see that this property must be true for any encoding. So now let's say something formal along these lines. Okay, so to be formal, it's much easier to work over GF2. So suppose we are given x1 up to xn in 0, 1, and want to check that the sum of xi mod 2 is equal to 0. Okay, so it's similar to what I said before, except now I want to work mod 2, it's linear. So what I ask for is okay. We will present a PCP for this fact, for this assertion. What's a PCP? It's a probabilistically checkable proof for the fact that sum of xi mod 2 equals 0. What will be this proof? For every S subset of n, okay, we will define ys to be what we said before. xi. Okay, and the mapping from the string of n bits to the string of, how long is this string y? It's 2 to the n bits. Okay, and this is n bits. Right, so this mapping is called, this is the Adamov encoding. this is y of x. Okay? So as proof, we ask for the Adamar encoding of x. And then I claim that there is a way to test that indeed the sum of xi is equal to 0. Okay, so given this y, we can test locally whether it encodes an x for which sum of xi equals 0 mod 2. Okay, so how do we test that? So notice that y of the set 1, 1, 1, 1, 1, 1, 1, the set n, okay, equals the answer, right? It's just supposed to tell us whether the sum of xi is 0 or not. Okay, I forgot to write mod 2 here. So one thing we can do is just read this bit, right? But then an adversary can just write whatever they want on this bit, and so it won't be, well, I don't necessarily have to trust this bit. So what I really need to do is first check that this encoding is valid. So I have two steps. Step 1, check validity of encoding. And step 2, read more correctly, decode the desired value from y. So I'll get to this in a minute. But first, let's just deal with this problem. I'm given a y. Someone claims that this y is the correct encoding of x, so that each ys is indeed the subset, the sum of a subset. Okay, and I need to check whether this claim is true or not. Okay, and I want to do this check by reading only a small number of bits from the proof. Okay. So at the same time, okay. Actually, we only have 5 minutes, so in that case, I can use the other board. Okay. Okay, so this task is known as linearity testing. Actually, instead of just showing the way this is equivalent to linearity testing, what you can do is do the following. Choose a random S, subset of n. So now it's more convenient, instead of thinking of S, to think of alpha in 0, 1 to the n. Okay, so S is like 1S is alpha. Okay, so 0 whenever the bit is outside of S, and 1 whenever it's in S. Okay, so choose just a random alpha. Choose independently at random some beta. And then you want to know whether y of alpha, which is the sum for all x's in alpha, plus y of beta, right? Am I doing this right? Okay. Equals y of alpha plus beta. Okay, so you have this vector of alpha, it's 1 somewhere, 0's other places, and this vector of beta. And when you saw bitwise the alpha plus beta, you add the mod 2. All the xi's that participated in two things disappear, just like they disappear here. So you expect this thing to hold. So check that y of alpha plus y of beta, all this equality is mod 2. So notice that this check, I used some randomness. So forget about this, just think of alpha and beta. I used some randomness to choose alpha and beta, but then I looked at only 3 bits from the proof. So that's pretty easy to do, right, in my phone bill. So I'm checking only these 3 bits. And the question is, what can I deduce from it? So certainly, if the encoding was correct, my check will always pass. In fact, this is easy to prove that claim all tests. So if the probability that the test succeeds is 1, this is exactly equivalent to saying that y is a legal encoding of some x. Okay? The more interesting thing is to say, well, I want that if this was something wrong, there was something wrong in this encoding, I want to be able to find it with constant probability. So if I'm only looking at 3 bits and the encoding is exponential size, I can't, someone can flip some bit somewhere, there's no chance that I will find it. But what we can prove is that if someone flips many bits and changes this encoding dramatically, then the probability to succeed is also going to change. So in this sense, this test is robust in the following sense. So usually, as we said before, if you have a system of equations and you look at all the possible solutions of this system, and then you say, okay, you know what? I'm going to take one equation and change it a little bit. Say flip it. It was a discrete system. You just change the value. And now, what happened to this set of solutions? Okay, so it is possible that such a small change will completely change the set of solutions, and you will have a completely different set of solutions, maybe no solutions or something like that. In a robust system, whenever you slightly modify the system of equations, it causes some slight modification in the system of, in the way the solutions look. So in this sense, what this means is that if this is a robust system, and there is a theorem that says that it is, it means that when the test passes with probability above, say, 99%, this can only have happened if the y is some 1% close to a good y. Okay, so it means you can move back and forth between how many of the equations you satisfy and how far you are from a good solution. Usually these are 2 different domains. It's the Hamming distance between solutions and the Hamming distance between how many equations are satisfied. And in a robust system, you can move back and forth between these 2 things. And there is a theorem that says that this is indeed true, and it takes a few minutes to prove this theorem, but I guess I didn't plan properly today, so I won't do it. But you can read it, it's written in many places. Okay, so this is some kind of small mini PCP theorem that shows how to check a linear assertion. It shows how to check, it's written all the way up there, that some sum of values equals something. Of course, a linear assertion doesn't encode all of NP, and it can be extended to be to encode all of NP, but this whole kind of direction has a serious drawback, and that is that the length of the encoding is huge, right? You have an assertion of n bits, the length of the encoding here is 2 to the n. This isn't feasible, and it doesn't answer our goal of mapping this G to this H over there, because this mapping should have been polynomial time. So I cannot encode G by some exponentially long H. I need to do a much more efficient thing, and this is what we'll talk about tomorrow and the next day. Okay.
Questions? Are there any questions? Yes.
A PCP that may not be NP?
A PCP that may...
P predicate that may not be NP?
Meaning that it encodes something that's stronger than NP?
P is the containment. I'm asking, is the containment proper?
Oh, I see. Yeah. Okay, so the question was whether I wrote NP is contained in PCP, and then I wrote the parameters. In fact, this containment is true also. Just because if a verifier just tosses a logarithmic number of randomness and reads a constant number of bits from the proof, since the number of random bits is only log n, the verifier can actually, in polynomial time, enumerate over all the possible coin tosses. So in NP, the verifier is stronger in the sense that it can read the entire proof, and it's allowed to run a polynomial number of steps. So certainly it can simulate such a verifier. That's a good point. Well, it's of course the reason is that it's a historic reason, right? It was defined before the equality was known, right?
The bottom containment is...
This is trivial. This part was not known, and this class was very interesting, and there's also various parameters, and people were very excited over this class and weren't sure how strong or weak it is. So
PC popular work was discovered that it's...
That's right. Yeah, I totally omitted any historic story here in this talk, but there's a very interesting story around it.
Are there other questions?
In the definition of PCP proof, we have a non-symmetric probabilities. In the positive case, the probability of success is 1. In a negative case, it's 1/2. Is it evident before we know the PCP theorem that it makes no sense to consider symmetric version with non-negative errors in both cases?
Okay, thanks. Excellent question. I should have mentioned it earlier. It's absolutely not obvious that this is the right thing to consider, and in fact, sometimes it's not the right thing to consider. So you can think of many variants of PCPs where the one there is just 2/3 and the no is 1/3, or different variants. And in fact, different variants correspond to different hardness of approximation results. Okay, so it's the C and the S in the gap CS problems. This 1.5. So it's just kind of conventional to write it this way, but certainly it can be different values. It's nice to expect from a proof system to be what's called complete, in that when a theorem is correct, you are certain that the proof is verified correctly.
Other questions? Thank you again.